Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a gentle pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from, and what time it is for you right now. From here, please take a moment to settle into a comfortable space, letting the edges of the day dissolve, and your mind drift somewhere quieter. In that soft place between waking and sleep, we can slowly turn our attention to something far beyond the immediate concerns of life. Something vast, quiet, and difficult to grasp, yet strangely soothing when we surrender to its immensity. That something is the universe, and the simple, ancient question of whether it ever comes to an end. People have wondered about the limits of reality for as long as there have been minds capable of lifting their gaze to the night sky. Even now, with spacecraft leaving tracks of data behind them and telescopes unfolding far beyond the Earth's atmosphere, the question remains unsettled. Does space stop somewhere? Or does it go on and on, silently stretching into regions that no light, no matter how determined, can return from? As we ease into this exploration, it can help to think of space not as an abstract scientific term, but as a quiet landscape that surrounds all things. Not crowded, not cramped, not hurried, simply there, unfolding in every direction. In the stillness of night, when the world is muted and small, it becomes easier to imagine ourselves as tiny passengers inside a much larger story. A story written over billions of years, where motion is slow and distance almost incomprehensible. When most people look upward, they see stars scattered like tiny points of fire across a black background. It is easy to assume that what you are seeing is the end of reality, a ceiling that holds the cosmos in place. But the truth is gentler and far more mysterious. Those points of light are not the surface of anything. They are not painted symbols on a dome. They are suns drifting through space, separated by empty regions so enormous that the spaces between them are more significant than the stars themselves. Even when you think of the night sky as a physical structure, it can be calming to remember that the darkness between stars is not emptiness in the normal sense. It is not the absence of existence. It is space itself, a quiet expanse through which light travels, taking years, centuries, or millennia to reach our eyes. The darkness is a presence, not a void. A place that stretches without resistance, as if it were designed for patience rather than speed. If you close your eyes and picture space, you might imagine it stretching outward like a wide, flat surface. But the universe is much more like an ocean without shores, where there is no fixed up or down, no center to anchor yourself to. Every point in space is a center, because space does not expand from a single location. Instead, all space expands at once, everywhere. The galaxies are not moving through a larger environment. The environment itself is stretching, carrying them along. This idea can feel heavy or confusing when approached quickly, but in the quiet of a slow explanation, it becomes easier to settle into. You can think of galaxies like boats on a lake, except the water is rising gently and uniformly, not from one edge, but from all edges at once. The boats are not accelerating outward. They are simply being carried as the lake beneath them becomes wider. In the observable universe, there are countless galaxies. Each one holds billions of stars, each star surrounded by planets, moons, and dust. And yet, despite all of this structure, what dominates the cosmos is emptiness. Vast, silent space, cradling everything in distances that seem impossible to map or measure fully. When astronomers observe this immensity, they are not only studying distant objects, they are studying the space between them. The question, does space end, is tangled with another quiet puzzle. Am I able to see everything that exists? And the answer is no. Not because telescopes are limited, or because distances are too great, but because space expands faster than light can cross it. There are regions so far away that their light will never reach us. Not in 1,000 years. Not in 1 trillion. Not ever. Those regions exist beyond what scientists call the observable universe. They are not absent, they are simply unreachable. It can feel oddly peaceful to realize that parts of the cosmos are permanently hidden from view. Not because someone is hiding them, but because physical law itself has boundaries. Light has a speed, space has a rate of growth. When those two truths meet, the result is a horizon, an invisible line beyond which information cannot cross. This horizon is not a barrier you would feel if you touched it. It is not a wall built by matter or energy. It is a kind of boundary shaped by time. The universe is about 13.8 billion years old. Light has been traveling for 13.8 billion years. So, the farthest we can see is the distance light has covered in that time. But the real universe extends beyond that, because space has expanded while the light has been moving. So, even though the age of the universe sets a finite window for visibility, the size of the universe might not be finite at all. It might have no edges. It might have no container. It may not even make sense to ask where it stops, because stopping is a feature of objects, not of space itself. If you are lying back in bed, listening to this as your breathing slows, you can picture space not as a bubble with solid walls, but as a continuous fabric, wider than sight, wider than imagination, and possibly infinite. An ocean with no shore, not because the shore is hidden, but because there may never have been one. Even so, people are drawn to the idea of an edge. Boundaries feel natural, because they help us understand our place. Rooms end. Cities end. Countries end. Even oceans have coasts. So it is easy to assume that everything must eventually give way to something else. That beyond the last star, there must be a frontier, and beyond that frontier, something different. But if you could float in the darkness between galaxies, drifting far beyond familiar clusters of stars, you would not find a wall. You would not reach a point where space stops and nothing begins. You would simply encounter more space and more darkness until you reached distances where expansion had pulled regions so far apart that nothing could travel between them, not even light. This calm, directional stretching of space is called cosmic expansion. It does not involve explosions or sudden movement. It is not fast in the way a car is fast. It is slow motion on a scale where slowness itself becomes extraordinary. Galaxies drift apart the way continents drift apart, only with more patience, spread across billions of years. If someone were to ask whether expansion will ever stop, the answer remains uncertain. The universe may continue stretching until galaxies no longer share the same night sky. Until stars burn out, planets freeze, and matter drifts apart until all that remains is a thin, cold haze of particles, spread so widely that no structure can form. This distant possibility is sometimes called heat death. It is not violent. It is not dramatic. It is a quiet fading where everything slows to a near standstill. Even this idea, with all of its melancholy, reflects a universe that is slow, patient, and vast beyond measure. A place where endings do not arrive suddenly. They unfold in silence across time spans longer than any human culture, language, or memory. As you rest, it may comfort you to know that none of this is pressing or urgent. The stars are not in danger tonight. Galaxies are not rushing away in panic. The cosmos is calm and will remain calm long after we have fallen asleep, long after our civilization has faded, and long after new ones may rise in our place. This gentle immensity is not something to fear, but something to accept. A reminder that the universe is not built for urgency. It unfolds on a timescale that gives everything room to breathe, even the stars. And somewhere, in that unfolding night, is the quiet possibility that space has no edge at all. Not because it hides its borders, but because borders may not apply to something that has no outside. If you look up at the night sky, it can feel timeless, quiet, unchanging, and ancient. But physics tells a different story. Space is not a still, empty backdrop. It behaves more like something soft and flexible, constantly stretching, shifting, and responding to forces we only partly understand. And the most astonishing part is that we didn't learn this from philosophy or imagination. We learned it from data. In the early 20th century, astronomers believed the universe was stable and eternal. It seemed reasonable. The stars looked permanent, the same each night, and nobody had observed galaxies moving around in any dramatic way. But the quiet stability of the cosmos turned out to be an illusion, one exposed through careful observation. Around 1912, astronomer Vesto Slipher began measuring the light coming from galaxies. He used spectroscopy, a technique that spreads light out into colors, a bit like sunlight passing through a prism. When he examined these light patterns, he noticed something odd. The spectral lines of many galaxies were shifted toward the red end of the spectrum. In physics, this redshift usually signals motion away from the observer, similar to how the pitch of a siren lowers as it moves away from you. But Slipher didn't immediately claim the universe was expanding. He simply reported careful measurements, unsure what they meant. Science often begins this way, someone quietly noticing something strange. Years later, Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory, measured the distances to these galaxies using Cepheid variable stars, a dependable type of stellar clock. Hubble discovered a clear relationship. The farther away a galaxy is, the faster it appears to be receding from us. This simple pattern became known as Hubble's law, and it offered the first robust observational evidence that the universe is expanding. It wasn't a theory imposed onto the data. The data revealed the pattern on its own. Modern science has built on Hubble's early work with highly advanced tools. Satellites like WMAP, Wilkinson Microwave Anisotropy Probe, the Planck Observatory, and the Hubble Space Telescope have mapped the cosmic microwave background, the faint afterglow of the Big Bang, with extraordinary precision. These maps don't just tell us that space is expanding. They tell us how fast, how smoothly, and how the expansion has changed over time. Measurements of distant supernovae, especially type Ia supernovae, have shown something even stranger. The expansion of the universe is speeding up. This unexpected discovery, made in the late 1990s by two independent research teams, earned the 2011 Nobel Prize in Physics. To explain this acceleration, scientists introduced the idea of dark energy, a mysterious form of energy that seems to push the universe outward. We don't know what dark energy is, but its effects are observable, measurable, and consistent across multiple independent experiments. Current estimates suggest that dark energy makes up about 68% of the universe. Dark matter makes up 27%. Normal matter, stars, planets, you, me, is only around 5%. It's remarkable to think that everything familiar, every atom you've ever touched, makes up only a tiny fraction of reality. Even though space is expanding, the idea of an edge is not as straightforward as imagining a boundary like a cliff or a wall. When scientists ask whether the universe ends, they often mean something more specific. Is the universe infinite? Or is it finite but unbounded? These are mathematically different possibilities. A finite, unbounded universe would be something like the surface of a sphere, limited in area but without an edge. If you traveled long enough, you could, in theory, end up where you started. Observations from the Planck satellite, especially measurements of cosmic microwave background curvature, suggest that on large scales, the universe is extremely close to flat. If that holds true everywhere, space might be infinite. But if curvature exists over scales too large to detect, the universe could be finite. The evidence isn't decisive. Space keeps some secrets. Even if the entire universe goes on forever, our observable patch does not. The observable universe is a spherical region about 46 billion light-years in radius, centered on Earth. Not because Earth is special, but because the observable universe is defined by what light has had time to reach us. The universe is roughly 13.8 billion years old, but because space has been stretching during that time, light from very distant regions comes from galaxies now much farther away than 13.8 billion light-years. This is a beautiful example of how observation forces us to rethink things that seem intuitive. Time, space, and distance behave differently on cosmic scales than they do in everyday life. Everything we know about the far universe comes from light. Radio waves, visible light, X-rays, microwaves, collected by telescopes on Earth and in orbit. We can't travel there, and we can't send probes. Our instruments simply listen. For faint emissions from hydrogen clouds, for supernova flashes in distant galaxies, for microwave ripples left over from cosmic infancy. The cosmic microwave background is especially important. First discovered accidentally in 1965 by Arno Penzias and Robert Wilson, it provided the first strong evidence that the universe began from a hot, dense state. Today, high-precision measurements of this radiation provide a kind of cosmic fingerprint of the early universe. The temperature variations in the CMB are incredibly small, about 1 part in 100,000. But they reveal patterns of density that later grew into all the galaxies and structures we see today. It's amazing to think that your entire existence may trace back to a small ripple in a plasma sea, 13.8 billion years ago. Many scientists suspect the universe extends far beyond our observable region. Some models predict there are regions so distant that light from them will never reach us, even with infinite time. This isn't because they're too far away right now, it's because the space between us is expanding faster than light can cross it. This doesn't violate relativity. Space itself can stretch faster than light travels through space. So, somewhere out there, beyond the soft horizon of observation, are galaxies forever disconnected from us. Not by emptiness, but by the changing shape of space itself. There is something quietly peaceful in that notion. Knowing that the universe contains stories we will never read, no matter how long we look. One of the most common misunderstandings is imagining the Big Bang as an explosion from a central point. But the best models we have suggest something different. The Big Bang didn't happen in space. It created space, which means there is no center, no point from which everything flew outward. Instead, every point is expanding away from every other point. Imagine dots on the surface of an inflating balloon. Each dot sees all the others moving away. None is the center. Our universe behaves similarly, at least in large-scale behavior. Local gravity, stars, galaxies, clusters, fights expansion. But on the biggest scales, space stretches, carrying galaxies along with it like leaves drifting apart on a slow, widening river. Even with modern data, cosmic expansion remains partly mysterious. We know that the universe expands. We know how fast. We can measure how the rate is changing, but we don't know why. Dark energy remains one of the biggest scientific puzzles of our time. Physics has answers, but also vast, silent spaces where answers are still forming. And strangely, that is not unsettling. It is peaceful. The universe does not rush to reveal itself. It unfolds at its own pace, just as we do. The unanswered questions do not undermine what we know. They give us room to keep learning. After all, science isn't the process of reaching final truth. It's the ongoing effort to understand more clearly than before. The strange thing about exploring the universe is that the more we observe, the more evidence we find that reality behaves in ways no one expected. For example, galaxies do not rotate the way they should. By all classical calculations, stars at the edges of galaxies should be flung outward, unable to remain bound by the observable mass. Yet they remain in stable orbits. Something invisible must be adding gravitational pull. This idea led to the concept of dark matter, not a poetic metaphor, but a physical substance that does not emit light, does not interact with electromagnetic fields, and cannot be seen directly. Scientists know it is there because its gravity shapes galaxies, the way wind shapes sand dunes, leaving patterns we can measure even if we cannot see the wind itself. Decades of experiments have tried to catch dark matter in action. Particle detectors buried deep underground attempt to isolate faint signals from hypothetical particles. Scientists send beams of particles through complex machinery, hoping something unusual will scatter or decay. So far, many experiments have returned null results, which is frustrating but also informative. Science is not just about confirming theories. Sometimes it is about ruling things out, narrowing the possibilities until only the true explanation remains. The fact that dark matter remains undetected does not mean it is imaginary. Most of the universe has always been hidden from us, and humans are still developing the tools needed to peel away those layers. There is an argument some philosophers make that humans evolved to survive on one planet, not to understand the machinery of cosmos. Our brains were sculpted to recognize patterns in foliage, not to comprehend quantum fluctuations. And yet, somehow, we push against that limitation. We build telescopes capable of seeing galaxies billions of light years away, where the light left before Earth formed. We build detectors that can sense the faint tremor of space-time when black holes collide. We create mathematics that allows us to describe gravitational waves, predict their signatures, and then listen for them through instruments so sensitive that passing trucks on nearby roads can disrupt the data. That humans can do this at all feels improbable and deeply hopeful. Science does not always offer comforting answers, but it often reveals an underlying harmony. When astronomers observe galaxies at different distances, they are also looking backwards in time. Light travels at a finite speed, so observing something a billion light years away means seeing it as it existed a billion years ago. This makes telescopes into time machines, capturing snapshots of ancient eras. We can watch galaxies collide, stars ignite from collapsing clouds, and even see remnants of the earliest light in the universe, known as the cosmic microwave background. That faint microwave hiss, spread across the entire sky, is leftover radiation from a time when everything was hot, dense, and uniform. It is extraordinary that a universe that began in such simplicity now contains structure, diversity, and beings capable of asking how it all happened. Many people assume science strips the universe of mystery, but the opposite is often true. A deeper understanding invites deeper questions. For instance, if the expansion of the universe is accelerating, what sets the rate of acceleration? Is it constant? Does it vary across time? Some models suggest dark energy may fluctuate, which means the universe could undergo different phases of expansion. Others speculate about entirely new fields or particles that influence spacetime on cosmic scales. The fact that multiple explanations remain viable highlights how early we are in this investigation. Standing at the edge of knowledge often feels like standing on a quiet beach at night. There is a sense of scale too vast to hold, and still, we lean forward to see more. The most human part of all this is that researchers continue working even when answers are slow, sometimes spending decades on a single experiment. They collaborate across continents, share data freely, and debated interpretations late into the night. There is uncertainty, disagreement, and sometimes disappointment, yet the work continues. It is a collective effort, shaped by people from different cultures, languages, and generations, all contributing to the gradual unfolding of knowledge. This stubbornness, this patience, is as much a part of science as mathematics or observation. Even in the face of cosmic indifference, people seek meaning in the act of discovery. Not necessarily cosmic purpose, but personal purpose. The satisfaction of understanding something previously hidden. The quiet joy of seeing a pattern emerge from noise. There is humility in realizing that the universe does not revolve around us, and comfort in recognizing that we are part of it anyway. The atoms that form our bodies existed inside stars that burned billions of years ago, and will someday become part of other structures, perhaps other worlds. Nothing is isolated. Everything participates in the ongoing story of matter and energy. It can be strange to think that the same physical laws that govern galaxies also guide the motion of cells inside a human body. Gravity shapes cosmic structure, while electromagnetism shapes chemistry, and chemistry shapes biology. Life does not stand apart from the universe, but arises naturally when conditions allow complexity to evolve. A star forms, lives, and dies, and in its final act produces elements needed for planets and people. From that perspective, existence is not an accident. It is a consequence of physical processes unfolding over time. Indifferent to outcome, but rich with possibility. Sometimes, when people learn how small humans are relative to cosmic scales, they feel insignificant. But smallness does not equal unimportance. Significance is not measured by size or duration. It is measured by experience, by connection, by the ability to care, to notice, to reflect. The universe may be enormous, but it has no awareness of itself. Humans do. That awareness, fragile, temporary, and easily overwhelmed, is still remarkable. We are not the center of the cosmos, but we are the part of the cosmos that can contemplate itself. At night, when the sky is clear, you can look up and see starlight that has traveled through silence and vacuum for ages beyond imagination. Some of that light began its journey before the Earth cooled, passing through regions of space where no life will ever exist. And yet, by chance, it ended up striking your eyes, a brief intersection of paths across deep time. In that moment, you become part of the story, not because the universe cares, but because you noticed. Even after decades of careful measurement and endless refinement, one question continues to echo through modern astronomy. If the universe is expanding faster and faster, what is it expanding into? And how do we even know it is accelerating at all? The answer is not found in dramatic explosions or cosmic fireworks, but in something surprisingly quiet. A tiny shift in the light of distant galaxies, so subtle that for most of human history, it passed completely unnoticed. And yet, hidden within that subtle shift was a message powerful enough to rewrite the fate of the cosmos. The signal arrived in 1998, when two independent research teams began studying a very particular type of exploding star called a Type Ia supernova. These supernovae are remarkable not because they are rare, but because they explode with almost identical luminosity each time. Astronomers sometimes call them standard candles, which makes them sound cozy, like lanterns lighting up the night sky, but in reality, they are thermonuclear detonations involving white dwarf stars reaching the limit of gravitational stability. Their destructive nature makes them scientifically perfect. You know how bright they should be, so if they appear dimmer, they must be farther away. That seems straightforward, but the universe rarely rewards simplicity. When researchers used these supernovae to map the distances of galaxies across space, the results contradicted everything the cosmological models predicted. Instead of slowing down under the pull of gravity, galaxies were racing apart faster and faster, as though some mysterious force were pushing them away. This was not just a minor error, not a small discrepancy you fix with a better equation. This was an existential challenge to physics itself. So naturally, scientists gave the unknown force an appropriately dramatic name: dark energy. It's funny, in a quiet sort of way, how often science gives intimidating names to things we don't understand. Dark matter, black holes, singularities. The names sound ominous, but they are really placeholders. Bookmarks left in the text of reality so we can come back when we know how the story ends. Dark energy is exactly that. A bookmark. Sitting at the page where the universe refuses to get smaller and insists on accelerating forever. The idea that the universe is accelerating suggests one of two broad possibilities. The first is deeply comforting. Perhaps the universe is infinite, stretching outward beyond any edge we could ever reach, with galaxies drifting apart endlessly across a boundless cosmic sea. There is something emotionally soothing in that image, like an endless ocean that never stops breathing. But the second possibility is less gentle and more unsettling. Perhaps the universe is finite, a kind of flexible balloon, and as it expands, the internal pressure builds, changing the texture of space itself until it becomes unrecognizable. The farther galaxies drift apart, the less communication is possible, not just technologically, but fundamentally. Their light becomes stretched and faded until even photons cannot bridge the growing gap. We tend to imagine cosmic isolation as a philosophical problem, but in this case, it might be a literal one. If the acceleration continues, then billions of years from now, most galaxies will be too far away for their light to ever reach us. Future civilizations, if they exist, may look up at a sky nearly empty and conclude, with certainty, that theirs is the only galaxy in existence. The universe will not end with an explosion or collapse. It will end with loneliness. Scientists do not express this outcome emotionally, of course. They use clinical phrases like heat death and cosmic horizon recession. But underneath those definitions is a very human feeling: the quiet sadness of impermanence. It is strange how science can produce a sense of melancholy without ever intending to. Still, the accelerating universe is not the only model. Some researchers propose that dark energy might evolve over time, weakening or strengthening. In one scenario called the Big Rip, dark energy becomes so powerful that it overcomes all other forces, eventually tearing galaxies apart, then star systems, then atoms, until even subatomic particles can no longer hold together. This sounds violent, but the timescale is almost unbelievably gentle. The tearing would occur slowly over billions of years, like an ancient tapestry fraying thread by thread. Imagine a sheet of ice melting molecule by molecule, not because of heat, but because the laws of physics themselves are shifting underneath it. Other models suggest a far calmer outcome. Perhaps dark energy will plateau, settling into a steady rhythm that allows the universe to expand forever without tearing itself apart. A universe that grows old but does not break. A universe that simply becomes larger, emptier, and more diffuse over time. Not a tragic ending, just a quiet one. And maybe that is fitting, because the universe has never been explosive by preference. Its loudest events are rare and brief. Most of cosmic history is silent, dim, and cold. One of the challenges in understanding the universe's fate is that we cannot step outside it to see the full shape. We are like fish in water, trying to describe the ocean without ever seeing the surface. Cosmologists attempt to infer the geometry of the universe by measuring the angles of ancient light. Specifically, photons from the cosmic microwave background, a faint fossil glow left over from the Big Bang. These photons were released when the universe was only 380,000 years old, long before stars formed, long before galaxies assembled, long before atoms settled into their familiar patterns. When we measure their distribution, we are peering into the baby photos of the cosmos, trying to reconstruct a childhood no one remembers. The most compelling evidence, based on data from missions like WMAP and Planck, suggests that the universe is flat. Not flat like paper, but flat in the sense that parallel lines never meet. This implies that the universe is infinite, or at least so large that we cannot detect its curvature. Yet even this conclusion comes with a whisper of uncertainty. Imagine staring across a vast lake so large that its curve is imperceptible. You might declare it flat, simply because your senses cannot resolve the slight bend of the horizon. The universe may be hiding the same curve from us, a curvature so subtle that no telescope can measure it, but still present, shaping the structure of space just beyond the reach of observation. It is possible that the universe loops back on itself, not like a sphere, but like a higher dimensional shape impossible to visualize. In such a universe, traveling in one direction forever might eventually return you to your starting point, though eons would pass before the journey completes. Science often touches the border of imagination in ways that do not feel like imagination, but rather like glimpsing a truth that language cannot quite hold. We try anyway, because the alternative is silence. Yet, for all our cosmic ambition, one of the most important insights in modern astronomy is how brief our window of knowledge truly is. We are alive at a moment when distant galaxies are still visible. Their photographs fill textbooks, documentaries, social media feeds, and the private memories of astronomers who have dedicated their lives to capturing faint signals from space. But future observers may not be so lucky. If dark energy continues its steady push, then much of the cosmos will eventually disappear beyond our observable horizon. Robert Caldwell, a theoretical physicist, once described this possible future as a universe of one candle left burning in an enormous dark cathedral. The imagery is not scientific, but profoundly human. It acknowledges the emotional dimension of cosmology, the strange way in which discoveries make us feel something, even when they are presented as numbers. Still, there is comfort in recognizing how much we have learned in the brief moment when the sky is still full of light. We know the age of the universe with reasonable precision, not because we counted years, but because we measured the temperature of ancient photons. We understand stellar evolution not because we watched individual stars grow old, but because we observed millions of stars at different stages, each one a snapshot of time. We mapped the large-scale structure of galaxies not because we traveled between them, but because gravity leaves handwritten signatures in the shape of the cosmic web. The universe is enormous and bewildering, but it is also strangely generous. It leaves clues scattered everywhere, fossils of light, patterns of motion, subtle distortions in the glow of background radiation. Each clue is a message encoded in physics, waiting patiently for beings capable of reading it. Maybe the most comforting idea, hidden beneath all this complexity, is that the universe does not demand certainty from us. It allows us to explore imperfectly, to make theories knowing they might be replaced, to ask questions that may never be fully answered. Knowledge, in this context, is not a monument but a journey, long, winding, and incomplete. Even the things we cannot explain directly, dark energy, dark matter, cosmic expansion, are invitations rather than barriers. They remind us that the universe is not finished revealing itself. There is more to discover, more to wonder about, more to feel curious or humbled or small or grateful for, and that, perhaps, is where science becomes emotional without meaning to. Not because it comforts us with certainty, but because it lets us stand quietly in the presence of something immeasurably vast, knowing that it existed long before us and will continue long after. Yet, somehow, we are still part of its story, even if only for a moment. It is difficult to predict which models will survive the next century of research. New instruments are being designed. New missions are being planned. New minds are entering the field, asking questions that earlier generations never thought to ask. Technology will reveal things we cannot imagine yet. Data will reshape theories. Paradigms will shift. But the human experience of looking up, wondering what is out there, and feeling a strange combination of insignificance and belonging, that will remain. Because no matter how abstract cosmology becomes, at its heart, it is an attempt to answer a very old question, whispered by countless people across countless eras. Where are we? And what does it mean to live in a universe so wide that most of it will remain forever beyond our reach? There is something deeply human about our desire to understand the universe not only as a physical structure, but as a meaningful place. We don't simply want to know how stars form. We want to know what that process says about us. We don't just catalog galaxies. We imagine living among them, or meeting something that does. Even scientific models, as precise and mathematical as they are, often carry a quiet emotional residue. Curiosity, humility, awe, sometimes fear, and often a subtle sense of longing. As though understanding the universe will somehow help us understand ourselves. A scientist rarely phrases it that way in a paper, of course. Academic writing keeps those inner movements hidden beneath equations and citations. But if you listen to the way people speak in private, or when they explain their research to students, you can hear the softer side of cosmology. The part that is not just about facts, but about belonging. That human layer becomes especially noticeable when scientists discuss the possibility of life elsewhere. Not because it is scientifically trivial, it is one of the most extraordinary questions we could ask, but because it carries emotional weight. It touches our sense of loneliness, our need for connection. Even the most rational thinker can't help but feel something when considering the idea that the universe might be full of minds, each seeing the cosmos from its own vantage point. But the search for extraterrestrial life has always been a paradox. On the one hand, it feels like an obvious expectation. There are trillions of stars, countless planets, vast spans of time. How could the universe not produce life more than once? On the other hand, the evidence is missing, not partially missing, but completely absent. Carl Sagan once described Earth as a lonely speck in the great enveloping cosmic dark. And that image still resonates with researchers because it reflects both wonder and uncertainty. The scientific approach to this question has shifted dramatically in the last few decades. For most of history, astronomers could only imagine what other worlds might look like. Now they can observe real planets orbiting real stars, using methods elegant enough to feel like science fiction. When a planet passes in front of its star, even by a fraction of a percent, the starlight dips. Instruments like Kepler and TESS track these dips with astonishing precision, measuring changes so small they would be invisible to the human eye. A distant world hundreds of light years away reveals itself not through images, but through a flicker. There is something poetic about that. Information arriving not as a picture, but as a rhythm. A heartbeat in the darkness, steady and predictable, betraying the presence of a world we cannot see directly. Once a planet is detected, the real challenge begins, determining whether it could support life. We look for what is often called the habitable zone, the region around a star where temperatures could allow liquid water to exist. But this definition is simplistic, almost childlike. Water is not enough. A world could sit in the perfect temperature range and still be barren, sterile, and overwhelmed by radiation or atmospheric toxins. Researchers refine this picture by studying exoplanet atmospheres through a technique called transit spectroscopy. When starlight filters through a planet's air, different molecules absorb different wavelengths, leaving fingerprints in the spectrum. From these fingerprints, scientists can infer the presence of gases like oxygen, methane, carbon dioxide, or water vapor. In some sense, they are trying to smell a planet from across the galaxy, detecting chemical scents carried on beams of light. But the search is not just biochemical, it is geological, atmospheric, chemical, temporal. A planet might be habitable now but sterile for most of its history, or vice versa. A planet might be covered in oceans but lack nutrients. It might be full of life but too distant or too dim for us to detect the signs. Even Earth would be difficult to identify from afar during much of its history. For billions of years, our planet was home only to microbes, and if an alien telescope had happened to observe us during that era, they probably would have concluded that Earth was lifeless. Sometimes, when scientists discuss these facts, they smile softly as if acknowledging a cosmic joke. We may discover thousands of planets, measure their mass, map their orbits, and still have no idea whether anything meaningful ever happened on their surfaces. Yet the search continues, not because we expect quick answers, but because the act of searching feels essential. In 2020, researchers announced that the Milky Way may contain as many as 300 million potentially habitable worlds. Not confirmed, just possible. A probability spread across unimaginable distances. We don't know whether any of them host life, but the number itself is enough to soften the existential loneliness that often accompanies cosmic thinking. It reminds us that Earth is not unique because it orbits a star, or because it has oceans. Earth is unique because life happened here. And if it happened once, maybe it can happen again. Some scientists argue that life may be common, but intelligence might be incredibly rare. The evolutionary path from microbes to minds is not straightforward. It is full of accidents, catastrophes, improbable transitions. The emergence of language, tool use, symbolic thought, All of it may depend on a particular sequence of events that could fail at any step. Evolution does not strive toward consciousness. Consciousness is a side effect, fragile and unnecessary from a purely biological perspective. And yet, here we are, fragile and unnecessary, but curious enough to build telescopes and launch spacecraft to send radio messages into the sky, to wonder whether someone else might hear them. We are, in our own gentle way, trying to make contact with the unknown. Not aggressively, not desperately, but almost shyly, like a child standing at the edge of a forest, calling out softly to see whether anything calls back. Perhaps that is why the universe feels both comforting and unnerving at the same time. It is vast enough to contain endless possibility, but quiet enough that the possibility remains uncertain. The silence we observe may be temporary or permanent, or simply beyond our current ability to interpret. Some scientists propose that advanced civilizations might communicate through technologies we cannot recognize. Others suggest they might not communicate at all, either because of biological constraints or philosophical choices. Communication requires energy, intention, and vulnerability is not always adaptive. There is an idea called the Great Filter, which suggests that somewhere along the evolutionary path from chemistry to intelligence, there is a barrier so difficult to overcome that most life fails. Some think the filter lies behind us, that the emergence of complex, tool-using intelligence was so improbable that it may not happen again. Others believe the filter lies ahead, that advanced civilizations inevitably destroy themselves before spreading into the cosmos. This model is not pessimistic by design. It is statistical. When you run simulations of planetary evolution across billions of stars, the emergence of stable, long-lasting civilizations often requires finely tuned conditions. Survival is not guaranteed, even for intelligent beings. Technology can outpace wisdom. Environmental change can outrun adaptation. Curiosity can create tools that overwhelm their creators. In that sense, the universe may not be hostile, just indifferent. But there is another possibility, gentler and more hopeful. Perhaps life, especially intelligent life, is rare simply because the universe is still young. Stars like our Sun are middle-aged. Low-mass stars, called red dwarfs, can burn for trillions of years, 10,000 times longer than the current age of the universe. If life prefers stable environments and long time frames, then the majority of cosmic biology may not emerge until far into the future, long after humanity is gone. In that model, we are early, not alone. Maybe we are one of the first civilizations to wonder about others, not because we are special, but because someone has to go first. And if so, then our role is not to find company, but to leave a trail of information behind. Messages encoded in spacecraft, radio waves, or artifacts, so that future minds, millions of years from now, can discover evidence that they were not the first spark of curiosity in the cosmos. There is something deeply comforting in that perspective. It replaces cosmic loneliness with cosmic responsibility, a responsibility to endure, to observe, to create, to send information into the future. Not because we expect a reply, but because participating in the universe is meaningful, even if no one ever thanks us for it. Scientific studies often frame these discussions analytically, but beneath the data is a quiet emotional truth. The desire for connection is one of the most enduring forces in human nature. It shapes friendships, cultures, religions, languages, and technologies. It shapes science, too, because science is fundamentally a conversation with nature, with history, with the future. It is easy to forget, in the complexity of cosmology, that our story began with not knowing. Before telescopes, before physics, before mathematics, people looked at the night sky and imagined gods, monsters, ancestors, spirits. Those stories were not primitive errors. They were attempts to humanize the unknown. Today, we use spectroscopy instead of mythology, but the instinct remains the same. We are still trying to turn the unfamiliar into something we can relate to. Astronomy, despite its technical sophistication, is still a form of storytelling. Every theory is a narrative. Every model is a sketch of reality. Every dataset is a collection of moments captured from the past. Starlight delayed by cosmic distances, arriving long after the source has changed or disappeared. There is a tenderness in knowing that the universe we see is not the universe of today, but the universe of ages gone. The light we observe is ancient. The stars we study may already be gone. The galaxies we map may already look different. We are not receiving live footage, we are reading history. And yet, this delayed vision does not diminish our understanding. It enhances it. It reminds us that the universe unfolds on timescales far beyond our lifetimes. And our role is not to witness the whole story, but to observe a chapter and pass it forward so someone else can read the next. Perhaps the most remarkable thing about the universe is not its size, or its age, or its mystery, but the fact that it can be understood at all, that we are made of the same atoms as the stars we study, that the laws governing galaxies also govern neurons, that consciousness, whatever it is, evolved not to solve cosmic riddles, but to survive, and yet it became capable of curiosity, introspection, wonder, and empathy. This suggests something profound, though not mystical. The universe produced beings who could ask questions about the universe. In that sense, life is not a disruption of physical law. It is an expression of it. And maybe that is why cosmology, even when framed in equations, feels strangely intimate. It is not just about what exists out there, but about how deeply we are connected to it. Every atom in our bodies was forged in the heart of a star. Every breath contains molecules older than the solar system. Every heartbeat relies on electromagnetic forces that operate the same way in distant galaxies. We are not observers of the universe. We are participants in it. Temporary, fragile, fleeting, but real. And if one day, far into the future, another intelligence emerges under another sky, looking outward with its own mixture of curiosity and uncertainty, perhaps it will feel something similar. A quiet recognition that being alive in a universe like this is not merely a physical event, it is a privilege. If you stay with the universe long enough, mentally or emotionally, you begin to notice a quiet pattern. The more we learn about it, the more uncertain we become. Knowledge doesn't collapse mystery, it expands it. Every question answered becomes a doorway to more intricate unknowns. This isn't a failure of science, it's a feature of reality. The cosmos is structured in layers, each revealing deeper complexity when peeled away. Scientists sometimes call this open-ended inquiry, but it might feel more accurate to simply say, the universe is endless enough that no one gets to finish it. there is something strangely comforting about that. Many aspects of life feel rushed, finite, pressured to reach conclusions. But in cosmology, there is no final exam, no complete explanation, just a continuous generational relay of curiosity. Each generation observes what it can, adds a few pieces to the puzzle, and hands the unfinished picture to those who come next. When we talk about the fate of the universe, we are imagining the last chapter of a story no one will be around to read. We theorize about heat death, the dissolution of galaxies, the evaporation of black holes. Not because we will witness these events, but because imagining the big picture helps us locate ourselves emotionally in the timeline of existence. It reminds us that everything that feels permanent, stars, planets, even atoms, is temporary. Temporary but meaningful. When cosmologists model the far future, they usually rely on thermodynamics. Entropy, the tendency of systems to spread out energy and lose structure, acts like a slow, universal tide. Over trillions of years, galaxies drift apart until even their light becomes too faint to see. Stars burn through their fuel, leaving behind white dwarfs, neutron stars, and black holes. Black holes slowly evaporate through Hawking radiation, releasing particles until they disappear. Eventually, the universe becomes a thin bath of low-energy photons, cold and quiet. This scenario is not dramatic or explosive. It is gentle. A slow dimming, a gradual quieting. Not an apocalypse, but a fade-out. When physicist Freeman Dyson wrote about this in the 1970s, he acknowledged not just the scientific reality, but the emotional impact. To him, heat death was not terrifying. It was melancholy, like the ending of a very long story. Others, like Brian Greene and Sean Carroll, have described it with similar softness. Not as cosmic tragedy, but as the final state of a universe that has done its job, transforming high-energy chaos into structure, life, and complexity, until no free energy remains to sustain difference. If that future seems bleak, remember that this kind of cosmic timeline is so long it makes recorded history look microscopic. Stars will continue forming for hundreds of billions of years before the decline even begins. Intelligent life might arise many times over before the universe becomes too quiet to support it. The story is slow, patient, and vastly bigger than human anxiety. It is possible that the universe will not end this way. Some models propose cyclic behaviors, big bangs and big crunches repeating forever. Others propose quantum tunneling events that reset space-time entirely. These ideas sound dramatic, but they emerge from mathematics, not mythology. The equations suggest possibilities because the universe is not bound to one narrative. Physics is not a story, but a landscape of potential outcomes. Whenever you step into this kind of speculation, you inevitably encounter another question. Why is there anything at all? Why does the universe exist instead of nothing? This is a question that lies outside normal scientific inquiry. Not because scientists avoid it, but because science operates best when it can test ideas. You can test gravity. You can test quantum mechanics. You cannot test nothingness. You cannot run an experiment on a universe that does not exist. Still, physicists try. They propose that perhaps the vacuum is unstable, that nothing is not truly empty, but a state full of potential, ready to blossom into space-time. They imagine quantum fluctuations that create universes spontaneously. They imagine that universes might replicate, like biological organisms, with physical constants that vary slightly each time. Some of these universes might produce stars and life. Others might remain sterile. Evolution, but on a cosmic scale. These theories are speculative, but they are not random. They are built from mathematics and consistency requirements, attempts to fill in a missing page in a notebook that is mostly coherent but incomplete. The difficulty of these questions highlights something we often overlook. Science is not merely a collection of answers. It is a habit of mind. A willingness to sit with uncertainty without collapsing into despair or fantasy. Scientists are not immune to existential emotions. Many of them simply channel those emotions through questions, models, observations. Curiosity is the emotional fuel that keeps science moving, even when the answers seem unattainable. You can see this emotional undercurrent in smaller, more practical research too. When astronomers measure cosmic microwave background radiation, the faint afterglow of the Big Bang, they are not just collecting data. They are listening to a whisper from the universe's infancy. Light that has traveled for 13.8 billion years, stretched by expansion, smoothed by time, arriving in the present as a map of primordial fluctuations. Those fluctuations, tiny variations in temperature and density, seeded everything. Galaxies, stars, planets, eventually life. If you look at a CMB map, you are looking at the origin of structure the moment randomness became order. The colors do not mean much to a casual observer, but to a cosmologist they are a childhood photo of the universe. There is a similar emotional richness when we study black holes. They are often portrayed as terrifying vacuum cleaners, consuming everything. But in reality, they are elegant solutions to Einstein's equations, places where space-time curves so steeply that nothing can escape. The fact that mathematics predicts their existence so cleanly is a reminder of how deeply logical the universe is. Even its extremes are not messy, they are precise. The discovery of gravitational waves, ripples in space-time caused by colliding black holes, confirmed this. When the LIGO Observatory recorded the first signal in 2015, the waveform lasted only a fraction of a second. A small chirp, barely detectable, representing two black holes merging over 1 billion light-years away. Something unimaginably violent, transformed into a tiny vibration in a mirror on Earth. There is a strange tenderness in that. The universe is loud, but its message arrives softly. Every scientific discovery with cosmic implications contains some quiet emotional truth. We learn that reality is vast, but also lawful. We learn that we are temporary, but not random. We learn that life's existence is improbable, but its emergence is natural given the right conditions. We learn that the universe changes, evolves, cools, expands, but does not rush. It moves on schedules so long they are almost meaningless to biological minds. We are built for seconds, days, and years, but the universe is built for billions of years, each filled with transformations that unfold slowly, inevitably, without urgency. If you ever feel pressure to solve everything quickly, remember that galaxies themselves took hundreds of millions of years to assemble. Complexity takes time. Stability takes time. Meaning takes time. The same is true for understanding. No one becomes wise instantly. No civilization becomes enlightened in a century. We are early in the story, even culturally, even technologically. Our telescopes are primitive compared to what future beings may build. Our understanding of consciousness, matter, and space-time is partial, promising but incomplete. But incomplete does not mean lacking value. The early stages of any story are still part of the story. Humanity may be a prologue, but prologues matter. Sometimes people worry that understanding the universe scientifically removes its mystery or emotional resonance. But the opposite is true. Mystery grows with comprehension, not ignorance. Understanding the mechanics of a sunset does not make it less beautiful. Understanding stellar nucleosynthesis, how stars forge elements, does not make existence less miraculous. It explains how physics can produce something as unlikely as a conscious mind that wonders about its own origin. There is a phrase often used in science communication. We are star stuff. It is poetic, but it is also literal. Every carbon atom in your body formed in the core of a star. Every oxygen atom spent time in a stellar furnace. Every calcium atom in your bones was sculpted by nuclear fusion. Matter does not simply exist, it cycles. The star that died billions of years ago so that you could breathe was not destroyed, it was transformed. On cosmic timescales, death is not an ending, it is recycling. This perspective might sound abstract, but it has practical emotional implications. People often feel small when they think about the universe. But it would be more accurate to say we are distributed. We are not isolated, fragile anomalies. We are part of a continuous physical process, one that began long before us and will continue long after. We are temporary configurations of ancient matter, borrowing atoms for a short period, arranging them into thoughts, memories, relationships, and stories. The atoms don't belong to us, we borrow them. The consciousness isn't permanent, we experience it. The universe is not something we visit, it is something we arise from, and that makes our existence meaningful, even if it is brief. People sometimes think science removes meaning, but in many ways, science reveals a more durable kind of meaning, one that does not depend on permanence or purpose or cosmic intention. Meaning arises not because the universe cares, but because living beings are capable of caring. Care is an emergent property of complex organisms. Curiosity is an emergent property. Love is an emergent property. These are not trivial byproducts, they are some of the most improbable behaviors ever produced by physics. Complex systems do not just compute, they feel. That fact alone is astonishing. The universe produced atoms that can experience beauty, molecules that can imagine, neural circuits that can grieve, hope, laugh, and share stories about galaxies as they fall asleep. Even if there are countless civilizations spread across billions of light years, or none, the existence of consciousness at all is extraordinary. Not because it is magical, but because it is unlikely and yet real. We often dream of finding other intelligent beings, not just for scientific reasons, but emotional ones. We want to know that somewhere out there, another mind is wondering, feeling, searching. But even if we never make contact, the existence of intelligence here, on this tiny planet, is enough to demonstrate that the universe is capable of remarkable things. Sometimes when people think about cosmic time frames, they worry that everything humans care about is insignificant. Science offers a different interpretation. Significance is not measured by duration or scale. A meteor lasts seconds, but reshapes a planet. A single mutation lasts a moment, but launches evolution in a new direction. A star lasts billions of years, but eventually fades into obscurity. duration is not the same as importance. In a universe where everything changes, meaning does not depend on permanence. What matters during a lifespan is not how long it lasts, but what it experiences. From a cosmic perspective, a species capable of recognizing its own impermanence is rare. A species capable of feeling grateful despite that impermanence is even rarer. A species capable of wonder, empathy, humor, storytelling, that is remarkable, even if it lasts only a few thousand years. Perhaps that is why thinking about the universe at night feels different than thinking about it during the day. The darkness softens the mind. The stars are visible reminders of scale, but also of connection. Pinpricks of ancient light, familiar despite their distance. They invite reflection, not because they are mysterious, but because they are silent. They do not explain themselves. They do not rush. They do not demand interpretation. They simply exist and allow us to find our own meaning in them. The search for understanding, scientific or personal, is not a race against time. It is not about reaching the end of the story. It is about participating in the story while we are here. Learning not because we expect certainty, but because curiosity is one of the privileges of being alive. Human beings have always told stories to make sense of existence. Today, we use physics and cosmology to build those stories, but the emotional impulse is the same. We want to know where we came from. We want to know where we are going. We want to know whether the universe is a hostile desert or a fertile sea. We want to know whether we are alone. Science may not answer those questions completely, but it gives us tools to explore them with clarity, humility, and care. It gives us a way to ask better questions. It gives us a way to notice patterns we would otherwise miss. It gives us a way to appreciate the universe not just as an environment, but as a process we are part of. Even when answers are incomplete, the act of seeking them can be deeply comforting. Curiosity is not a sign of ignorance. It is a sign of engagement. Wonder is not childish. It is one of the most sophisticated emotional responses a mind can have. As you think about the universe, its age, its size, its mystery, you don't need to resolve anything. You don't need to solve the cosmos before you fall asleep. You don't need to reconcile physics with emotion. It is okay to let uncertainty remain. It is okay to let the mind loosen its grip on big questions. The universe does not demand resolution. It allows us to rest inside the unknown. Somewhere, right now, galaxies are moving apart at incredible speeds. Stars are forming inside nebulae. Planets are cooling, oceans condensing, atmospheres stabilizing. Life may be beginning on distant worlds, or it may not. We cannot know yet. The universe does not hurry. On Earth, nighttime arrives quietly. Your body softens. Your thoughts drift. You remember things or forget them. You breathe. You rest. You exist, briefly, beautifully, as a conscious fragment of a vast physical process. There is no need to force meaning onto the cosmos. Meaning happens on its own, in small gestures, short conversations, simple acts of care. The universe may last trillions of years, but experience happens moment by moment. Tonight is one of those moments. Temporary, like everything. Precious, like everything. You are made of ancient materials shaped by improbable events, capable of thought, connection, and curiosity. Whatever happens to the universe in the far future, whatever mysteries remain unsolved, whatever civilizations may rise or fade, the fact that you are here Now, thinking about existence is remarkable enough. So rest. Let the universe continue without you for a while. It knows how. It has been doing it for billions of years.